Okay, today I'm going to talk about Chapter 10, Periodicity. Okay, Part 1, Physical Properties, Trends of Period 3, Theory. Okay. Sorry about this. Let me move here. Okay. Now, for the learning outcomes, what we are to learn is we are going to learn about atomic radius, ionic radius, melting point, and electrical conductivity of elements of period 3 only. With that being said, let us name all of period 3 elements. First one is sodium, magnesium, period 3, aluminium, silicon, phosphorus, sulfur, chlorine, argon. So these are the 8 elements we're going to study. We're going to study 2 parts. Part 1, we're going to study about the physical properties of them all. So we're going to look at these 8 elements and see how they differ one another. Is there any trend? And not only are we going to study the trend, we are also gonna explain qualitatively. That means we need to analyze them, be it in their structure, or in any other factors that can explain the difference between the 8 elements among their physical properties. Next, we are going to explain the variation in first ionization energy. So we are going to explain the variation in first ionization energy. So that's also one thing we're going to do. And again, more explanation, and hopefully our explanation of all those also include bonding and electronegativity. Now, first, we're going to look at atomic radius. Hold on for a moment. Sorry about this. Maybe put somewhere here. Smaller. Now, for atomic radius, if we analyze, from sodium all the way to argon, the atom become smaller and smaller. Now, why did it become smaller and smaller? Let us analyze this. Atomic radius becomes smaller and smaller because first, sorry, Alright, here. First, the number of protons and electrons increases across the period. However, when the electrons increase, same electron shell remain at the electron shell number 3. Therefore, shielding effect remains constant. Distance, becomes smaller because the greater attractive force, your nuclear charge increases, causes the electron to become closer. So therefore, distance of the outermost electron become lesser. The size determined by the where the outermost electrons are, right, becomes smaller. Okay, so the size of the atoms becomes smaller. Okay, that's relatively straightforward. Okay, next, ionic radius. Now, let us clarify when we talk about ionic radius. We're now comparing between the elements. But I want to clarify one thing. When we talk about ions, we are talking about this sodium plus magnesium. Hold on, do this again. Sodium plus magnesium 2 plus, aluminium 3 plus, silicon 4 plus, phosphorus 3 minus, non-metal already, except electrons, 2 minus, and of course argon, there is no value to it because argon does not become an ion. So if we analyze the first 4 cations, it decreases. When we analyze the anions, it decreases. Okay, both of them decreases. Why is that so? Okay. But one more thing also to note, not only that both trend is decreases, the anions are larger than the cations. The anions are larger than the cations. So we need to analyze two things. First, the decrease in both cations and anions, and why anions is bigger than cations. Now, if we look at this, right, ions versus original atoms ions, the positively charged ions from sodium plus and Si4 plus become smaller because when you donate the electron, effectively lost the outer shell of electrons. Okay. For P3 minus and Cl minus, they are larger than their original atoms, gain extra electrons, more repulsion. The distance between the outermost electrons and the nucleus increases. That is why anions is bigger than cations. Just to clarify further, sodium is 1s2, 2s6. P3 minus 1s2, 2s2, 2s6, 2p6, 3s2, 3p6. One shell, full shell bigger. And that is why anions is always bigger than their cations. For anions, bigger than the original atoms. For cations, smaller than the original atoms. Now, for the trend, right, ionic radius becomes smaller for the very same reason like the atomic trend. Which is what? Which is the number of protons increases, but the electrons are added to the same shell. Therefore, shielding effect remain constant and the distance between the electrons, outermost electrons, and the nucleus decreases. So, ionic radius becomes smaller. Same thing apply for the trend from P3 minus to Cl minus, increasing positive nuclear charge, but the electrons are still added to the same electron shell. Ions become smaller. Now, if we look at this, right, we realize that the electronegativity of period 3 increases across the period. Okay. Now, why is that the case? Before we go on, what is electronegativity? Electronegativity is, let me put it here. It's the ability of an atom to attract the bonding electron pair. How strong does it pull the electrons? Okay. Oh, sorry. If we learn about this, we know it increases across period 3. But why? We acknowledge number of protons increases. Again, positive nuclear charge increases. However, the number of electrons being added, or the electrons, bonding electrons, are always on the same shell. So what happens then? Whenever period 3 elements, let's just say they form a covalent bond across the period, the nuclear charge will always increase. However, the outermost electron is always used to bond with other elements that always remain on the same shell. Again, similar to atomic radius and ionic radius, shielding effect remains constant. Therefore, key point to note, attraction between the bonding electrons and nuclear charge increases. That's about it. Okay, so therefore, as time goes by, the attraction becomes stronger and stronger across a period. Now, this is melting points of period 3. Okay. If you notice, this trend is a little bit different. Yeah. First, it goes up. Melting point increases. Then, it goes down. And then, weirdly enough, there's a small increase right here. What is happening? Yeah. So we analyze, first melting point increases, then it decreases. And there's a small increase right at the middle. Okay. We're going to analyze one by one. Let's analyze the increase first. Okay. Now, please remember, melting point does not depend on the interaction between one atom and another. It depends on the intermolecular forces between one molecule and another molecule, or one compound with another compound. Please remember that. So therefore, if we analyze first the sodium, magnesium, aluminium, the key reason... sorry about that. Okay, now I'll put somewhere here. Okay. The key reason, it is because all three of them metals all got metallic bonding. So all makes sense. Sodium, magnesium, aluminium metals all got metallic bondings. That means they are cations surrounded in a sea of delocalized electrons. Okay? The difference lies in that melting point depends on metallic bonding. Aluminium having the strongest, highest melting point means aluminium have the strongest metallic bonding. But how come? It is because, okay, let us talk about sodium. Okay, sodium, when it donates out the electron, it becomes sodium plus and 1 electron. Magnesium, on the other hand, become Mg2 plus and 2 electron. Aluminium, on the other hand, becomes Al3 plus and 3 electrons. And that's the difference. Metallic bonding is between the cations and the number of electrons. First, the number of electrons of aluminium is the highest, 3 donated out. Second, look at aluminium. Aluminium is 3 plus. The charge highly positive. Highly positive charge with a lot of electrons around it. Metallic bonding, high attraction, strongest among the 3. So this is very clear so far why it increases. But what happens to silicon? Why is silicon the highest among them all? It is not metal after all. For that, it is because silicon is what we call giant covalent structure or giant molecular structure. Silicon element, the structure, it means that all of it, when it's connected, it is all pure, strong covalent bonds. So it means that between silicon to silicon, it has the strongest attraction among all of them because it is pure, strong covalent bond. Therefore, it is the hardest to melt among the rest. Oh, I would like to modify a bit. This is not intermolecular forces, my mistake. Sorry. I want to modify this. Not intermolecular forces, I like to call it interparticle forces, which is actually, or intra-particle forces between silicon to silicon, pure covalent bond. Okay. Now, what about the rest? The rest makes sense. Suddenly all become low melting point. Why? Because all of them are nonmetals. Nonmetals exist as small covalent molecules, okay, but therefore their intermolecular forces is actually weak van der Waals forces. Now, so it's understandable why is it weak van der Waals forces. But sir, how come decreases? For that, you need to analyze. It's very simple. S8P4Cl2. What does it mean? It turns out phosphorus doesn't exist as phosphorus alone. It exists as a molecule called phosphorus 4, P4. Sulfur exists as S8 and chlorine exists as Cl2. Now, you may be wondering how does S8 exist as a covalent bond S8? It exists like this. S bonded to this S, bonded to this S. So this is actually an S8 molecule. Now, so now it makes sense, okay, why it has low melting point because of van der Waals forces. But why it decreases, or why suddenly S8 become sulfur have the highest melting point among this all, right? It is because although all 4 of them is van der Waals forces, my question to you is this. Which one has the most electron? Yeah, we go with this. most electrons. Let us categorize them. Who is number 1, number 2, number 3, number 4. Number 1 spot is actually S8. Number 2, P4. Number 3, Cl2. Number 4, argon. Because S8, sulfur oxide S8 has the most electrons, therefore among the 4 non-metal elements of period 3, it will have the highest melting point among the 4. Because it has the most electrons, therefore its van der Waals forces will be the strongest. Followed by P4, followed by Cl2, followed by argon. Okay. Now we are going to study about the electrical conductivity of period 3. Okay. Now, phosphorus, sulfur, chlorine, argon, close to 0 electrical conductivity. Silicon has a little bit, which I'll explain later, and sodium, magnesium, aluminium is what we call have a relatively high electrical conductivity. And the biggest reason behind it all is because sodium, magnesium, aluminium are metals. They have metallic bonding, therefore they have free moving delocalized electrons for the current to go through it. Now, non-metals are not able to conduct electricity, but silicon is able, because silicon is what we call like a semi-metal. Have you heard of the phrase semiconductor industry? Silicon is actually what we call semiconductor, able to conduct a little bit only, and that a little bit is what we use to one of the basic foundations for computers. That's why it is called Silicon Valley, because the basics of computer, one of the components is transistors. One of the elements to make transistors is silicon. So therefore, it's called Silicon Valley. Okay. I think that's quite clear so far. Now, let's talk about the first ionization energies of period 3. You have sodium, magnesium, aluminium. Okay. Okay. You have silicon, phosphorus, sulfur, chlorine, argon. Okay. Now, first it rises up. Let us analyze this. Okay. Rises up in general. The only 2 things that's happened is when there's a drop right here. Okay. Does this graph look familiar to you? It is because we have discussed this in chapter 3, where we talk about first ionization energy trends across a period. The same trend applies also for period 3. Okay. Okay. Now, what is first ionization energy? First ionization energy is the energy needed to remove 1 electron out. Okay. So therefore, it increases across period 3. Now, because of that, why it happens? Because let us analyze the 3 factors. Again, same thing right there. First, positive nuclear charge increases. However, the electron removed come from the same shell. Sorry, this is of an older one. Does not remain constant. It decreases. Oh, the distance between the nucleus and the outermost shell electrons decreases. Okay. So we analyze the second factor. Distance decreases. Next, what other factors? Shielding effect. Shielding effect remains constant, therefore force of attraction increases because three factors, remember. Nuclear charge increases, distance decreases, shielding effect remains constant. The attraction between the nucleus and the outermost electrons increases, making it harder to remove that electron. Therefore, first ionization energy of period 3 elements increases across the period. Now, we're going to talk about the two drops right here. From magnesium to aluminium, drop. From phosphorus to sulfur, drop. Why? The reason behind it is because the outer electron in aluminium is in the 3p subshell, whereas the magnesium one is in the 3s subshell. Therefore, for aluminium, the distance between the outermost electron and nucleus increases slightly. Why? 3p versus 3s. 3p a little further, 3s a little closer. Shielding effect increases slightly. Why? Because 3s face shielding effect from 1s, 2s, 2p. 3p faces shielding effect from 1s, 2s, 2p, and 3s. Because of this, the two factors beat the slightly increased nuclear charge, overcome that, the forces of attraction decreases. Electron a little further, shielding effect a little higher. Beats the increased nuclear charge, causing the forces of attraction to decrease. Okay, and the ionization energy drops, making it easier to be removed. Phosphorus and sulfur does not have this issue because one is in 3p, the other also in 3p. However, take note that the outermost electron in phosphorus is from an unfilled orbital, a singly filled orbital, whereas the one to be removed in sulfur is from a paired orbital, a filled orbital. Because of this, oh, sorry, I accidentally removed yes, sorry about that. Oh, sorry. Because of that, what happens is that the extra repulsion from the paired electrons in the sulfur, because it's in a paired orbital, results in less energy needed to remove the electron. This effect is what we call spin pair repulsion. Okay, this effect is for what we call spin pair repulsion. Okay, And that's why there is a drop from phosphorus to sulfur. Oh, okay. So now let me clarify. Let's go back to the learning outcome. Are you able to explain the trends in atomic radius? What's the trend? Decreases. Ionic radius. What's the trend? Cations and ions decreases. Okay. Are you able to explain that trend? Melting point. Increase, then decrease. Other than sulfur highest among the nonmetals. Electrical conductivity. Metals high. Silicon medium. Or poor, relatively, but still got a little bit. And non-metals none. And last but not least, are you able to explain the variation for first ionization energy? With that being said, I'm done. Thank you very much.